This is the second lecture of green technology. Today, in this lecture, we are going to study about the concept of energy, what's kinetic energy, and different forms of kinetic energy. And then we are going to study about the concept of electromagnetism. So, let us begin. What is energy? If you look around, is anything moving? Can you hear, see, or feel anything? Surely you can. This is because something is making something happen, and most probably there is some power at work. This power or ability to make things happen is what we call as energy. It makes things happen. It makes change possible. Energy moves cars along the road and makes aeroplanes fly. It plays our music, heats our rooms, lights our homes. Energy is needed for our bodies, together with plants to grow and move about. With the above explanation in mind, let us study more. Energy can be stored or transformed from one place to another, or object to object in different ways. Energy has different forms. Two major forms of energy are kinetic energy and potential energy. Potential energy is the energy possessed by a body by the virtue of its position relative to others, stresses within itself, electric charge, and other factors. An object can store energy as the result of its position. For example, the heavy ball of a demolition machine is storing energy when it is held at an elevated position. This stored energy of position is referred to as potential energy. Similarly, a drawn bow is able to store energy as a result of its position. When assuming its useful position, that is, when not drawn, there is no energy stored in the bow. Yet, when its position is altered from its usual equilibrium position, the bow is able to store energy by virtue of its position. This stored energy of position is referred to as potential energy. So, we can say potential energy is the stored energy of position possessed by an object. Another is kinetic energy. What is kinetic energy? All moving things have kinetic energy. It is the energy possessed by an object due to its motion or movement. These include very large things like planets and very small ones like atoms. The heavier a thing is and faster it moves, the more kinetic energy it has. Now let us see some of the illustration of various potential energy and kinetic energy. Here are some of the examples of potential energy. The first example of potential energy is that of gravitational energy. The energy an object or substance has because of its position, anything up high. Another example is that of stored mechanical energy. Energy stored in an object by application of force must push or pull on an object. Another example is that of nuclear energy. Energy stored in the nucleus of the atom holds the nucleus together. Another example is that of chemical energy. Energy stored in the bonds between atoms hold molecules together. These were some of the simpler examples of potential energy. Now we'll see some of the examples of kinetic. Kinetic energy, as explained earlier, is the energy an object has because of its motion. If we want to accelerate an object, then we must apply a force. Applying a force requires us to do work. After work has been done, energy has been transferred to the object, and the object will be moving with a new constant speed. The energy transferred is known as kinetic energy, and it depends on the mass and speed achieved. Kinetic energy can be transferred between objects and transformed into other kinds of energy. For example, a flying squirrel might collide with a stationary chipmunk. Following the collision, some of the initial kinetic energy of the squirrel might have been transferred into the chipmunk or transformed to other forms of energy. So let us look at some of the other forms of kinetic energy. For example, mechanical energy. or you can say motion, movement of objects or substances from one place to another. Electrical energy, movement of electrons in one direction, sound energy. Movement of energy through substance in the form of longitudinal compression waves. Radiant energy, electromagnetic energy that travels in transverse waves. Thermal energy, or you can say heat, internal energy of a substance due to the vibration of atoms and molecules making up the substance. So, we saw some of the examples of potential and kinetic energy. You can again see in this chart we have forms of energy. There are two forms, potential and kinetic energy. Potential energy is the stored energy, and kinetic energy is the energy caused due to the motion of waves. So some of the examples of potential energy are chemical energy, nuclear energy, stored mechanical energy, gravitational energy, and some of the forms of kinetic energy are radiant energy, thermal energy, motion, sound, electrical energy. Now, after getting the basic concepts about the energy, now we have to understand what's electromagnetism. Electromagnetism is popularly known as science of charge and of the forces and fields associated with charge. In electromagnetism, there are two facets. First is electricity and other is magnetism. Electricity and magnetism were long thought to be as separate forces. It was not until 19th century that they were finally treated as interrelated phenomena. Albert Einstein's special theory of relativity established beyond a doubt that both are aspects of one common phenomenon. At a practical level, however, electric and magnetic forces behave quite differently and are described by different equations. Electric forces are produced by electric charges, either at rest or in motion, while as magnetic forces, on the other hand, are produced only by moving charges and act solely on charges in motion. Electric phenomena occur even in neutral matter because the forces act on the individual charged constituents. The electric force in particular is responsible for the most of physical and chemical properties of atoms and molecules. It's enormously strong compared with gravity. For example, the absence of only one electron out of every billion molecules in 270 kg person standing 2 meters apart would repel them with 30,000 ton force. On a more familiar scale, electric phenomena are responsible for the lightning and thunder accompanying certain storms. Electric and magnetic forces can be detected in regions called electric and magnetic fields. These fields are fundamental in nature and can exist in space far from the charge or current that generated them. Remarkably, electric fields can produce magnetic fields and vice versa, independent of any external charge. A changing magnetic field produces an electric field, as the electric physicist Michael Faraday discovered in work that forms the basis of electric power generation. Conversely, a changing electric field produces a magnetic field, as the Scottish physicist James Clerk Maxwell deduced. The mathematical equations formulated by Maxwell incorporated light and wave phenomena into electromagnetism. He showed that electric and magnetic fields travel together through space as waves of electromagnetic radiation, with the changing fields mutually sustaining each other. Examples of electromagnetic waves traveling through space independent of matter are radio and television waves, microwaves, infrared rays, visible light, UV rays, X-rays, and gamma rays. All of these waves travel at the same speed, namely the velocity of light. They differ from each other only in frequency at which their electric and magnetic fields oscillate. An important aspect of electromagnetism is the science of electricity. which is concerned with the behavior of aggregates of charge, including the distribution of charge within matter and the motion of charge from place to place. Different types of materials are classified as either conductors or insulators on the basis of whether charge can move freely through their constituent matter. Electric current is the measure of the flow of charge. The laws governing currents in matter are important in technology, particularly in the production, distribution, and control of energy. A static distribution of charge produces an electric field. Charge in motion, that is an electric current, produces a magnetic field. Electric current is an example of charge or electrons in motion. If we arrange a wire in a coil and run a current through it, it produces magnetic field that looks like a bar magnet, called an electromagnet. Putting a real magnet inside it can shove the magnet back and forth depending on the current direction, called the solenoid. Some of you who do not know what's electromagnet is a magnet that is created using an electric current created by electricity. It can even be weakened and strengthened by decreasing or increasing the current. Electromagnets are used in all kinds of electric devices, including hard disk drivers, speaker motors, generators, as well as in scrap yards to pick up heavy scrap metal. They are even used in MRI machines, which utilize magnets to take photos of your body. Motors and generators are vital to everything we do in the modern world. A motor takes electrical energy and uses a magnet to turn the electrical energy into motion. A generator does the opposite. It takes the motion and uses it with a magnet and generate electricity. Now let us get ourselves familiar with some of the basic concepts of electromagnetism. Everyday modern life is persuaded by the electromagnetic phenomena. When a light bulb is switched on, a current flows through a thin filament in the bulb. The current heats the filament to such a high temperature that it glows, illuminating its surroundings. Electric clock and connections link simple devices of this kind into complex systems such as traffic lights that are timed and synchronized with the speed of vehicular flow. Radio and television sets receive information carried by electromagnetic waves traveling through a space at the speed of light. To start an automobile, currents in the electric starter motor generates magnetic fields that rotate the motor shaft and drive engine pistons to compress an explosive mixture of gasoline and air. The spark initiating the combustion is an electric discharge which makes up the momentary current flow. There are several laws governing these. Let us look up some of the fundamental laws. First law is Coulomb's law. Many of the devices and phenomena are complex, but they derive from the same fundamental laws of electromagnetism. One of the important of these is Coulomb's law, which describes the electric force between charged objects. Formulated by the 18th century French physicist Charles Augustin de Coulomb, it is analogous to Newton's law for the gravitational force. Both gravitational and electric forces decrease with the square of the distance between the objects, and both forces act along a line between them. In Coulomb's law, however, the magnitude and sign of the electric force are determined by the charge rather than the mass of an object. Thus, charge determines how electromagnetism influences the motion of charged objects. According to the Coulomb, the electric force for charge at rest has the following properties. First, like charges repel each other, unlike charges attract. Thus, two negative charges repel one another, while a positive charge attracts a negative charge. Second, the attraction or repulsion acts along the line between the two charges. Third, the size of the force varies inversely as the square of the distance between the two charges. Therefore, if the distance between the two charges is doubled, the attraction or repulsion becomes weaker, decreasing to 1/4 of the original value. If the charge comes 10 times closer, the size of the force increases by the factor of 100. Fourth, the size of the force is proportional to the value of each charge. The unit used to measure charge is Coulomb. If there were two positive charges, one of 0.1 Coulomb and second of 0.2 Coulomb, they would repel each other with a force that depends on the product. If each of the charges were reduced by 1/2, the repulsion would reduce to 1/4 of its former value. Static cling is a practical example of Coulomb's force. In static cling, garments made of synthetic material collect a charge, especially in dry winter air. A plastic or rubber comb passed quickly through your hair also becomes charged and will pick up bits of paper. The synthetic fiber and the comb are insulators. Charge on these objects cannot move easily from one part of the object to another. Similarly, an office copy machine uses electric force to attract particles of ink to the paper. Another fundamental principle is that of charge conservation. Like Coulomb's law, the principle of charge conservation is a fundamental law of nature. According to this principle, the charge of an isolated system cannot change. If an additional positively charged particle appears within a system, a particle with a negative charge of the same magnitude will be created at the same time. Thus, the principle of conservation of charge is maintained. In nature, a pair of oppositely charged particles is created when a high energy radiation interacts with matter. An electron and a positron are created in the process known as pair production. Electric current is a measure of flow of charge, as for example, charge flowing through a wire. The size of the current is measured in amperes and symbolized by I. An ampere of the current represents the passage of 1 coulomb of charge per second. A current is positive when it is in the direction of the flow of positive charge. Its direction is opposite to the flow of the negative charge. The force and conservation laws are only two aspects of electromagnetism. However, electric and magnetic forces are caused by electromagnetic fields. The term field denotes a property of space so that the field quantity has a numeral value at each point of space. These values may also vary with time. The value of electric or magnetic field is a vector, that is, a quantity having both magnitude and direction. The value of the electric field at a point in a space, for example, equals the force that would be exerted on unit charge at that position in space. Every charged object sets up an electric field in the surrounding space. A second charge feels the presence of this field. The second charge is either attracted towards this or repelled from it, depending on the sign of the charges. Of course, since the second charge also has an electric field, the first charge feels its presence and is either attracted or repelled by the second charge too. The electric field from a charge is directed away from the charge when the charge is positive and towards the charge when it's negative. If the positive charge were placed in the electric field, it would feel a force in the direction of the field. A negative charge would feel a force in the direction opposite to the direction of the field. If anybody has any queries, they can email me on following email address. Thank you.